close that one. And not that one. That one. That one. And that one. Solving exponential equations that require the use of logarithms to solve them. We did 2 or 3 really nice exponential equations last time leading up to example 2D, where we took the natural log of both sides in order to solve that. Example 2E is considerably more involved, but let's look at the process that we would use to do this. Example 2. Going to see if we can solve this exponential equation. No need for the capital there, but this is 4.5. I would like to begin by using some sort of logarithm. You could use a base 3 logarithm or base 4 logarithm, but it's recommended to use a logarithm that you have a special button on your calculator. For evaluating for simplicity, it'd be best to do that. So either a natural logarithm or the LOG, base 10, common logarithm would work. What I typically use is the natural logarithm because it's 2 letters to write for each log rather than 3 letters to write, and that's, well, doesn't take as long. Also, for the f part when we get to it, the base will be the natural base e, and that works a little bit better with the natural logarithm than it does with the common logarithm. The e base shows up more often than the base 10, so for that reason, I'll just use natural log all the time. So the natural log of 3 to the power of 2x plus 5 equals the natural log of 4 to the power of 3x minus 2. We have 3 key properties for expanding and condensing logarithms that we can use. We'll use those a little bit more when we solve logarithmic equations later in this section. But it's property number 3 on the list that we did log base a of m to the r. What we said was that r can come out in front, and we have r times log base a of m. So just like this exponent, log of an expression raised to a power, that exponent comes out in front. That's kind of the benefit of taking the log of both sides. This 2x plus 5 comes out in front of that logarithm, and the 3x minus 2 comes out in front of that logarithm. And it transforms this from being an exponential equation with the variables up in the exponents, really, because these are linear expressions, 2x plus 5, 3x minus 2, it transforms it into a linear equation. Now it involves some logs, but they're just logs of constants rather than logs of variables. Since 2x plus 5 is a binomial, I put it out in front. I'm not going to be quite right if I don't enclose that in parentheses. It's that entire quantity multiplied by the log, and it's the entire quantity 3x minus 2 multiplied by this log. So it's a linear equation. If I were to solve this graphically and graph y equals the left-hand side and graph y equals the right-hand side, I'd have 2 straight lines. And it'd be a matter of finding the point, if there is one, where those 2 straight lines intersect. But we'll go ahead and do this algebraically. Let's clear the parentheses so we can try to get the x terms together. Multiply the 2x by the natural log of 3, and then put the plus symbol. Multiply the 5 by the natural log of 3. Same thing on the right-hand side. The 3x gets multiplied by the natural log of 4. And minus 2 times the natural log of 4. Not the friendliest looking linear equation you've ever solved. But when we boil it down, there are 2 terms that have x's in them. There's that one right there that has an x, and that one right here there that has an x. And there are 2 that I would refer to as non-x terms. There's that one that does not have an x, and that one that does not have an x. The terms that have x's in them, since it's a linear equation, need to get together on one side of the equation. So those with the red boxes around them need to get together on one side. I'm going to say the left-hand side. And the ones with green boxes around them need to get together on the right-hand side so that we can express one side as x times an expression, times a constant expression, and then we'll be able to solve it for x. So let's subtract 3x times the natural log of 4 from both sides. And while we're at it, of course this will cancel these, while we're at it, let's subtract also 5 times the natural log of 3 from both sides so we can isolate all the x terms on one side of the equation. And that will cancel that 5 natural log of 3. On the left then, we'll get 2x times the natural log of 3 minus 3x times the natural log of 4 equals negative 2 times the natural log of 4 minus 5 times the natural log of 3. I think I'd like to continue working my way down this, so I'm going to add another page and then kind of have that for reference as we continue solving this on the next page. Left-hand side, each term has a factor of x. Right-hand side, no x's at all. What's the next thing we can do on this left-hand side? Since each term has a factor of x, we can, well, we'd like to be able to combine the like terms, but the logs, the log of 3, log of 4, really kind of prevent us from doing that. It's almost like, we don't do that much with radicals in this class, but it's almost like having a couple terms where one of them has a square root of 2 in it, and the other one has a square root of 3 in it, and we really can't add them together because they're not like radicals. Well, here we have different logarithms, so what we can do is we can factor out an x. We can write this as x times 2 times the natural log of 3 minus 3 times the natural log of 4. So if you were to take that now and distribute the x through the parentheses, it would give us back what we had in the step right up above it. The right-hand side, if you wanted to, now if I asked for a show of hands, not many hands would go up, but if you wanted to, you could condense these logarithms into a single logarithm. You could factor out a negative sign, you could take the 2 and make it an exponent on the 4, you could take a 5 and make it an exponent on the 3, and then you could squish the two logarithms together. Sum of the logs equals the log of the product, but we don't have to do that. The calculator, when we punch this into a calculator, calculator's not going to care whether it is two different logarithms that are being subtracted or a single logarithm. So I'm going to leave it just like it is and just copy and paste negative 2 natural log of 4 minus 5 times the natural log of 3. Now, it looks way more complicated than an equation like, what, 10x equals 25. Doesn't our equation look way more complicated than this equation? But really, that's kind of what it is. This is a number times x equals a number. And here what we have, this is a number times x equals a number. So all we have to do, like here, we would divide both sides by 10. Right here, we just need to divide both sides by the coefficient of x, which is 2 natural log of 3 minus 3 natural log of x. So that's kind of messy there. I'll redo that. But let's divide both sides. I feel like I should copy and paste it down below there. Divide both sides by 2 times the natural log of 3 minus 3 times the natural log of 4. And on the right-hand side, that's going to be the value of x. These divide out, a little one there, and x equals negative 2 times the natural log of 4 minus 5 times the natural log of 3 over 2 times the natural log of 3 minus 3 times the natural log of 4. And it's a matter of punching that into the calculator and coming up with a decimal approximation, maybe taking the time to check it because there are a lot of places to make a careless mistake, a sign mistake here and there. So we'll see if the calculator confirms what we suspect is the solution. So scoot this over there. And we type it into the calculator a lot like when we did those rational functions and graph those. Need to make sure and enclose the numerator in parentheses and also enclose the denominator in parentheses. In pre-calculus right now, I'm working in sequence mode, so I have to go back and change this to function mode. There we go. And there. Second, quit. So to type this in, hopefully I won't make a mistake. For the key, press history. Press the left parenthesis to begin the numerator, and then the negative 2 ln 4. Close the parentheses for the logarithm, and then minus 5 ln 3. Close the parentheses for the logarithm, and then close the parentheses for the numerator, divided by, open parenthesis, for the denominator, 2, natural log of 3, close the parentheses for the log, minus 3, natural log of 4, close the parentheses for the log, and then close the parentheses for the denominator. I'm going to press enter, and if it looks like it works, I will snip that and paste it on this page. I believe this is the correct answer. So let me see how much of this. Let's do this instead. Snip this much. 4.2136 if we're going with 4 decimal places. X is about 4.2136. Is there a good place to paste all that? Ooh, right there probably would work. A little smaller maybe. If we wanted to check this, to feel a little bit more confident so we sleep better at night knowing that, that we found the correct answer, what we would do is go back to the original 3 to the 2x plus 5 equals 4 to the 3x minus 2. Substitute 4.2136 for x in each of those places and see if it gives us approximately the same number on both sides. Now it won't be exactly because this is an approximation to the solution, but if we go with 5 significant figures, 4.2136, each one of those figures is significant, then they should agree to the first 5 significant figures in each of those answers. So let's try 3 to the power of 2 times 4.2136 plus 5, and see what we get for that. This is going to be a pretty good sized number. 2,549,191.792. And then if we go with 4 to the power of 3 times 4.2136 plus, minus 2, thank you. We should expect the 2, the 5, the 4, and the 9, 2, the 5, the 4, and the 9 to be the same. Maybe the 1, or maybe it'll be a 2 there. That should be pretty close. After that, I really don't have a lot of expectation that it's going to agree to the nearest 10 or to the nearest 1, and it should come close to agreeing to the nearest 100. Let's see what we get. They do agree to the nearest 100, and they are off. They do not agree to the nearest 10, but that's fine because 1, 2, 3, 4, 5. If we were to round both of these, this would be 2,549,200, and this would be 2,549,200. So if we rounded both these to 5 significant figures, then they would be as close as they need to be based on where our answer is. If we had included the 03 there, the O3 right there, then they should agree to the ones place. They should agree to 7 significant figures rather than just 5. But this is all that I was going for in that case. So 4.2136, I'll put it in set notation, 4.2136, since it is the rounded solution to this equation. Let's look at the next one. The next one doesn't take quite as long. That was probably a good one to start the class with because we're not exhausted yet. Now we're exhausted. So the next one shouldn't be so bad. I want to solve this. Now first, what I want to say is don't do this. And then I'm going to show you what not to do. Now, this is not technically wrong, but it may lead you to do something that is technically wrong. So suppose we start off just like we did this one, and that one we did at the end of class last time by taking the log of both sides. That's not wrong. The natural log of 4e to the 0.75t equals the natural log of 21. That's not wrong, and I can actually get where I need to go by doing this. The next thing that I'm likely to do, if I take the log of both sides here, though, is wrong. If I take the 0.75t and bring it out in front, this would be a really great ABCD question, but I've kind of stopped doing that this semester. What's wrong with this? Why am I not allowed to take that 0.75t and bring it out in front?
Because the ln has to be up front.
ln.
The ln has.
It needs to have a. The ln doesn't need to be a number in front of
Yeah,
it.
exactly.
Yeah.
Because you're timesing it then, correct?
Right. It'd be a number times the log. It turns out that that's okay. It would be okay to have something in front of the ln in this case. There's a because it's a t because it's an unknown. Turns out that's okay. It's okay to have the unknown. It's less than 1.
It looks better the way it is.
It looks better the way it is.
I think it has to do something with the e.
The e, if it were like a 10 or a 2, maybe. Turns out
because I think the number e can easily convert into ln though.
Yeah, the ln and e have a real nice relationship with each other. But that turns out not to be the key issue which would cause this to be wrong. But there's a serious issue here that makes this wrong.
Decimal?
The decimal's actually okay.
Jiminy Christmas.
What could it be? Well, the exponent on the other side. The 21's okay, turns out. There is one number here that causes this to be a problem. What is the number?
4?
It's the 4. What's wrong with the 4 and where it is and its relationship to everything else that causes this to be a problem?
It's in between the ln and the e.
It's in between the L and the E. The issue with the 4 is that the E is raised to the 0.75t power, but the 4 is not raised to the 0.75t power. If we had parentheses around the 4e, which we don't, if we had parentheses around the 4e, then it would be fine. The natural log of an expression raised to a power, that power comes out in front. But this is not the log of an expression raised to a power. This is the log of a product. And the log of a product is equal to the sum of the logs. So instead of taking that 0.75t out in front, it would be correct if I would write this as the natural log of 4 plus the natural log of e to the 0.75t, and then I could take that 0.75t and bring it out in front at that point.
So is that where we end up when we do it the way you say do this?
It's going to look a little different. It's going to look a little different. That we're going to deal with the 4, but we'll deal with it a little differently. So I'm going to clear this screen of everything that's here, and let's suggest a different way to go about it. Here goes. Goodbye. The 4 is going to be a problem, so let's deal with the 4 so it's not a problem. What's a suggestion of something we could do with that 4?
Divide it first.
Let's divide both sides by 4. So when the coefficient of the exponential expression is not 1, when possible, divide both sides by that, and that's going to get you on a better track. So this is going to be e to the 0.75t equals 5 1/4. That's not a quarter. 5.25 or 5 1/4. So now, with 1e to the power of 0.75t rather than 4e to the power of 0.75t, it's going to work well for us to take the log of both sides.
Because you can put it in front.
Yes. That, and maybe even a better reason than that, but definitely that. You can bring it in front. Natural log of e to the 0.75t equals natural log of 5.25. Now, there are two ways that we could explain that this left-hand side just turns into 0.75t. Way number 1 is we take the 0.75t out in front, which is totally okay in this case, 0.75t times the natural log of e, with or without the parentheses around the e. What is the natural log of e? Calculate on your calculator. It's 1. Natural log of e is the power that e can be raised to get e as the answer. What power can e be raised to get e as the answer? Well, e to the first power equals e. So that's one way to see it. Another way is simply to do this. This was in our, remember the Jeopardy stupid answer properties of logarithms? The natural log of e to a power is just that power. The natural base and the natural logarithm are inverses of each other. Natural exponential function and natural logarithm are inverses of each other. So if you'd have x, it needs to be positive, but the understanding is that t is, no, it doesn't have. It can be any real number. I'm sorry, we're doing the exponential function first. Take any real number, raise e to that power, follow it up with a logarithm that tells you the power that e was raised to, so it gives you the x. So 0.75t equals the natural log of 5.25, and then it's just a matter of dividing both sides by 0.75 and punching into the calculator. T equals the natural log of 5.25 divided by 0.75. Natural log 5.25. And again, very important, close the parentheses after the 5.25, otherwise it's going to divide the 5.25 by 0.75 and then take the log, and that's not what you want. Take the log, divide by 0.75, and get how to round it. I've been going with 4 decimal places, and that's probably a good rule of thumb unless my math lab specifically asks for a different number of decimal places. You know how that goes. So I'm looking at the 9, the 7 is 1 to the right of the 9, the 7 says go up. That pushes the 9 up to 0, which pushes this 0 up to a 1. So 2.2110. T is about 2.2110, I believe. Does that look okay? Rounding to the 10,000ths place, 4 decimal places.
Can we look at something on the notes part?
This one, yes. Okay. So these are our exponential equations that we can look at. Next, we want to look at some logarithmic equations. General guidelines for solving logarithmic equations. There'll be some of these where we're taking the log of expressions that are just too complicated to deal with, and it might be that we have to do some sort of graphical method or numerical method rather than an algebraic method. And if so, we could go back to the intersection of graphs method or the x-intercept method from chapter 1 and use the calculator. But if it's one that we can solve algebraically, it's going to boil down to one of 2 situations. If we have logarithms on either side of the equation, we'll want to condense all the logarithms together as much as possible. Have as few logarithms as possible on the left, as few logarithms as possible on the right, and until we rewrite the equation into one of two forms, either, and let's just go with another page here. Either this form, log base b of m equals n, if you have nothing but logarithms, and in addition to a logarithm, just a number. Then condense all the logarithms together, put them on one side, and take that number and put it on the other side, and write it in the form log base b of m equals n. Now, if b is just a number, no x's, just a number, and n likewise is just a number, when we rewrite this in exponential form, that look like a W, not really. Rewrite this in exponential form. Go to logarithmic form to exponential form. The base is b, so that's the power that's not the power. That's the number that's being raised to a power. The power is what's equal to the logarithm. N is what's equal to the logarithm, so n is the exponent. And then, since n is the power that b can be raised to get m as the answer, when we take b and raise it to the power of n, we get m as the answer. So this is the equivalent exponential form. If n is just a number and if b is just a number, now this equation could still be really, really complicated, but it's only as complicated as m. If m is a polynomial, then we have a polynomial equation. If m is a rational expression, then we have a rational equation. If it's more complicated than that, we're just going to pull out a calculator, graph y equals the left-hand side, y equals the right-hand side, and hope we can find a point of intersection. So this is one approach. The other approach is this. Suppose you have nothing but logarithms, no additional terms. Condense all the logarithms on the left-hand side into a single logarithm. Condense all the logarithms on the right-hand side into a single logarithm. And then do something like what we did with the exponential equations. You remember when we had 3 to the x equals 3 to the 4th power, we were able to say that since the bases are the same and the expressions are equal to each other, the exponents have to have the same value like that. Same sort of thing. The logarithm function is 1 to 1, just like the exponential function is 1 to 1. So we can say m equals n, effectively dropping the logs. So if we have logs on both sides, and they have to be to the same base, so we might have to change the base. Hopefully we don't, but if we were going to use this property, we'd have to write them as logs with the same base. Then we could just set the arguments equal to each other, effectively dropping the logs and just solving the equation m equals n. Okay, so we'll look at least one of each of these, maybe two of one of them. Solve each equation. Example 3, the A part has been done for us. So let's look at the B part.
But can you explain, let's see, it's not a solution. Oh, okay.
Yes, let me comment on that because for this one that we're going to run into, we're going to have a similar sort of thing show up. These properties of logarithms we're going to use in order to write it in the form that we want. Log of an expression equals a number. We may get extraneous solutions. We may get a number that satisfies, see this negative 13 halves satisfies this equation right here. Well, that's an expression. It satisfies that equation. You substitute negative 13 halves for x. It makes the left-hand side 0. So it satisfies that equation. Negative 13 halves satisfies that equation. It'd be kind of a pain to plug that in, but it would. It satisfies that equation. It satisfies that equation. And it even satisfies that equation. It does not satisfy the original equation because of a domain issue with the logarithm. If I take negative 13 halves and multiply by 2, I get negative 13. If I subtract 5 from that, I get negative 18. We can't take the log of negative 18. If we do, we get an imaginary number, and so we just don't do that. So since negative 13 is not in the domain of these logarithmic expressions, it can't be regarded as a solution to this equation. So when we say this sum of the logs equals the log of the product here, we're assuming that the values of the variable that give us the x plus 2 and the 2x minus 5, it makes those expressions positive. Negative 13 doesn't do that. So although it gives an equation down here that has this as a valid solution, it's not a valid solution to the original. We'll see the same sort of thing with example 3b. We have the sum of two logarithms. So we're going to use the property log base a of m plus log base a of n equals log base a of m times n. Sum of the logs equals the log of the product. And rewrite this as log base 4 of 2x minus 2 times x plus 3. I think I mentioned last time, don't think of it as factoring out the log or whatever, because if you think of it like that, you'll probably end up with a plus in between those expressions rather than multiplying them together. So they really need to be multiplied together inside there. Now we have this, not trying to make anybody dizzy, but now we have this expression, log base b of m equals n. Log base 4 of that quadratic expression equals 3. So we can take that and rewrite it in exponential form. So back, scrolling down again. Okay, now I'm there. What's the base? 4 is the base. Now 4 needs to be raised to the exponent. The exponent is what's equal to the logarithm. So 4 needs to be raised to the third power. And when 4 is raised to the third power, we get 2x minus 2 times x plus 3. At this point, we have transformed it from a logarithmic equation to what kind of equation? Anybody know what kind of equation this is? It's going to be a quadratic equation. When we simplify the right-hand side, we'll get an x squared term and an x term and a constant term, just a number on the left-hand side. So this is going to be a quadratic equation. What is 4 times 4 times 4? 64. On the right, we FOIL, we get 2x squared. There's going to be a 6x for the O terms and a minus 2x for the I terms. And that works out to be 4x plus 4x and minus 6 on the end. What's the next thing to do if we're trying to solve a quadratic equation? Set it to 0. Subtract 64 from both sides, that'll set it to 0. 0 equals 2x squared plus 4x minus 70. Before we pull out the quadratic formula, let's at least consider the possibility that we may be able to factor this. What should we do if we're thinking about factoring this? If we could go directly to the AC method and think product of negative 140 and sum of 4, and I think that we could find such numbers, but let's factor out the 2, and it might be simpler than that. X squared plus 2x minus 35. That way we just have to think product of negative 35 and a sum of 2. What numbers make that happen?
5 and 7.
5 and 7. Let's make the bigger one positive. So x minus 5 times x plus 7. When we FOIL, we get positive 2x in the middle, negative 35 on the end, x squared in front. And then set each factor equal to 0. The 2 doesn't give us any solutions because 2 is never equal to 0. X minus 5 may give us a solution, x plus 7. When we set that equal to 0, that may give us a solution. So scratch out the 2 equals 0. X equals 5 satisfies the equation. X minus 5 equals 0. x equals negative 7 satisfies the equation. X plus 7 equals 0.
You can't have a negative in that.
The fact that it's negative doesn't automatically disqualify it, but it kind of leads to the disqualification, because if we take negative 7 and put it here, 2 times negative 7 equals negative 14. Negative 14 minus 2 is negative 16, and we don't take the log of negative 16. Likewise, negative 7 plus 3 is negative 4. Don't take the log of negative 4 either. So for those two reasons, either one would have been enough. Scratch the negative 7. This is extraneous. It does not give us extraneous. Yeah, there we go. It does not give us a solution to this. So it's just the 5. Now the 5, we ought to check that too. It's possible we could substitute 5 for x, and it still make one of these arguments negative. You don't know what I'm pointing to. I'm pointing at these. It could mean that it still makes one of these negative, but it doesn't. 2 times 5 is 10. 10 minus 2 equals 8. We could take a log of 8. 5 plus 3 equals 8. And again, we're taking the log of 8. Evidently, log base 4 of 8 is half of 3, because we have to add log base 4 of 8 to log base 4 of 8 to get 3. So evidently that's equal to 1.5. You could confirm that a couple different ways, by solving a type 1 exponential equation, or by using the change of base formula. Where's that calculator? If I wanted to use the change of base formula to confirm that log base 4, this is almost a little bit off topic here, but it's related. Log base 4 of 8, how does that work? You pick a logarithm, any logarithm, maybe the natural log, and you take the log of the argument and divide it by the log of the base. And I think that's 1.5. Natural log of 8 divided by natural log of natural log of 4. That's what we divided by, and we get 1.5 as the answer. So you don't have to go that far in the process of checking it. All you have to do is confirm that this number, this potential solution, doesn't make either one of these arguments negative. And to see why the negative 7 actually showed up, negative 7 is a valid solution to this equation and this one and this one and this one and this one and this one, and it even satisfies this equation. How does it satisfy that equation? Negative 7. Put a negative 7 here, and it makes this negative 16. Put the negative 7 there, and it makes that negative 4. And then what do? Negative 16 times negative 4 is positive 64. And log base 4 of positive 64 equals 3. So that way, when you multiply those two negatives and get a positive, it actually does satisfy this equation, but not the one right up above it. So we can't count it in the final solution set. Just the 5. How would you solve this graphically if you were if you wanted to solve it graphically? Could you do this? You'd have to use the change of base formula to convert the base 4 logarithms, so that you could use the or to convert the log, so you could use the base 4 logarithms. It would look something like this. Log base 4, you would say natural log of 2x minus 2 divided by natural log of 4 plus natural log of x plus 3 divided by the natural log of 4. If you graph y equals the left-hand side and y equals the right-hand side, the two graphs should intersect at a point that has an x-coordinate of 5. Does that look like a hard thing to do or an easy thing to do?
Is that in my math class?
It could be used. I don't think I've given you any problems that require that you solve them graphically. So this is just basically lagniappe as far as we're concerned, a little something extra. So y equals natural log of 2x minus 2 close the parentheses, and divide by the natural log of 4, plus natural log of x plus 3. It's good practice with the change of base formula, though. Divided by the natural log of 4. And then for y2 equals 3. I think if I zoom 6, there'll be definitely a point with an x-coordinate of 5, and the y-coordinate has to be 3 because it's the horizontal line, y equals 3. So the two graphs should intersect in the point 5, 3. Zoom 6. The domain of the left-hand side only goes as far to the left as positive 1 because the 2x minus 2 has to be positive. And the other one, of course, is the horizontal line. So I guess there's an additional amount of trickiness if you go second calc 5 to find the point of intersection, and you want to let the logarithmic expression be the first curve. You press enter. See, a lot of times what you do is enter, 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 and it'll find it. But you press enter repeatedly, it won't find it because when the calculator starts out in the standard viewing window, it starts out in the middle, which is 0. And 0 is not in the domain of that log expression. So what you have to do is actually work your way to the right just a little bit until x is at least 1. And you see that cursor flash on the screen. Then it will let you select it, enter. And then the second curve, enter. And then a guess. It should find it even if I press enter a third time. And it should find the point 5, 3. So the x-coordinate is 5. Okay. Next logarithmic equation. Example 4. Natural log of x plus 2 minus natural log of x minus 1 equals natural log of 2 plus natural log of 2x minus 7. So there are more logs, but there's nothing other than the logs. There's not a constant term out there. So since they're all natural logs, and there's nothing else, condense the two logarithms together on the left, condense the two logarithms together on the right, and then we're going to be able to drop the logs when we do that and just set the arguments of those logs equal to each other. On the left, we have the difference of two logs, so we want to use the property log base a of m minus log base a of n equals log base a of m over n. Difference of the logs equals the log of the quotient. Turns into division when we squish the logarithms together and compare the arguments. So this is going to be the natural log of the fraction x plus 2 over x minus 1. On the right-hand side, it's the sum of the logs, and the sum of the logs is the log of the product. So it's going to be the natural log of 2 times the quantity 2x minus 7. One logarithm on each side. The logarithms are equal to each other and they have the same base. They're both natural logarithms. So we can set their arguments equal to each other. X plus 2 over x minus 1 equals 2 times the quantity 2x minus 7. And however one would solve an equation such as this is what we have. So we'll solve it. What would you do next? A couple things we might try. It's a rational equation officially because we have rational expression on the left-hand side, polynomial on the right. We don't care for fractions, do we?
Nope.
So how do we deal with the fractions?
Multiply both sides.
So multiply both sides by x minus 1. Honestly, I should have copied and pasted that down there, but I didn't, so I'll live with it. For the sake of space, divide out the x minus 1s, and we have x plus 2 equals, I should probably go ahead and multiply this out a little bit. I'm going to distribute the 2 across the parentheses to get 4x minus 14. And then next we'll need to FOIL that with the x minus 1. This is going to be a quadratic equation. It is a quadratic equation, but to solve it, we need to simplify the right-hand side completely and then get 0 on one side. So here goes. X plus 2 equals 4x squared. We're looking at a minus 4x for the outer terms, a minus 14x for the inner terms. So I'm thinking minus 18x. and then plus 14 on the end. Just going to copy and paste that up there in a manner of speaking. We need 0 on one side. So I just put what was on the right on the left and put what was on the left on the right. I interchanged the two sides. Flipped them, swapped them. Now I'm thinking about getting 0 on the right-hand side.
So you subtract the x.
So subtract x, subtract the 2. So effectively subtracting that quantity, x plus 2. We get 4x squared minus 19x plus 12 equals 0. Pull out the quadratic formula or try to factor this. Is this a scary one to try to factor? The AC method shouldn't be too painful. Because I think I can think of two numbers you can multiply together and get 48 that add up to negative 19. But if in practice you would probably go to the quadratic formula here rather than taking a moment to think about factoring it, we could do that instead. Would you rather do the quadratic formula? Okay. So here goes. X equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. X equals 19 plus or minus the square root of, I want to say the square of negative 19 is 361. Does that sound right? Mm-hmm. So whatever 361 minus 192 is that 16 times 12? 192 is 16 times 12. So we've got to subtract. And what do we get when we subtract?
169.
Good, that's a perfect square. So it's going to be x equals 19 plus or minus the square root of 169 all over 8. X equals 19 plus or minus 13 all over 8. Everyone good with the fact that 13 times 13 equals 169? Now, quick show of hands. Don't shout out the answer, but who knows what 19 plus 13 is? Most of us do. And what 19 minus 13 is? Yes, okay. So we can simplify this, in other words. We wouldn't want to leave our final answer like this. We can write x equals 19 plus 13 over 8, or x equals 19 minus 13 over 8. So x equals, now we have to think of it. 32? Ugh, just missed it. 32 over 8, or x equals 6 over 8. So x equals 4, or x equals 3/4. Two possibilities. Now we should check them and make sure they both make the arguments of the logarithms positive. In order to be a valid solution, it has to be in the domain of these logarithmic expressions. So first check the 4. 4 plus 2 is 6. We can take the log of 6. 4 minus 1 is 3. We can take the log of 3. 2 times 4 is 8. 8 minus 7 is 1. And we can take the log of 1. So 4 looks good. We will include that in our solution set. Next, 3/4. 3/4 plus 2 equals 2 3/4. We can take the log of that because that's positive. 3/4 minus 1 is negative 1/4. And we don't take the log of negative 1/4. So 3/4 is not good, not in the domain. So scratch it. It's extraneous. And our solution set only includes the 4. Just the 4. Because this one does not require the change of base formula to solve it graphically. That might be a good approach with this one as well. But we won't do that. Instead, let's look at this last one. Should probably get almost there in 7 we have the difference of the logs. To condense the difference of the logs, this is going to be the log of what? Log of the quotient. X plus 4 over x minus... You said quotient? I'm so sorry. That's exactly right. It sounded like difference from way up here, so yeah. Yeah, that's exactly right. Log of the quotient equals 3. All right. Natural log literally means log base e. So you don't have to write this if you know exactly what you're doing. But I think it may be helpful if I just write what ln means. It means log base 3. Sorry, log base e, not 3. Close to 3, but not 3. Log base e of the expression equals 3. Rewrite this in exponential form. What's the base? It's e. So e is going to get raised to a power. What power? E to the third power equals that quotient, x plus 4 over x minus 1. You could punch up e cubed on a calculator. It's about 20. But if you're going to do that, you need to keep track of at least 3 or 4 decimal places. So the final answer can be expressed correct to 3 or 4 decimal places. So I would say just hang on to the e cubed. It may seem awkward, but it's actually less awkward than dealing with 19 point something or 20 point something, whatever it is. Let's multiply both sides by x minus 1. That will enable us to divide out the x minus 1 from the denominator. And we'll have x plus 4 on the right and this is actually going to be a linear equation with an awkward coefficient of e cubed in there. So I'm going to go ahead and distribute the e cubed across the parentheses right up above this. I'm going to say x times e cubed equals x e cubed, and negative 1 times e cubed equals negative e cubed, so that we have x e cubed minus e cubed on the left. Like we did, if you're prone to motion sickness, hang on while I scroll and then I'll tell you when I'm done. So blink. Like we did way up. Oops, I went too far. Keep your eyes closed. Where is it? It was way up here. There it is. I was right the first time. We had a term with an x, a term with a constant, a term with an x, a term with a constant. The terms with x's in them had to get together on the left-hand side. The terms that did not have x's had to get together on the right-hand side. Going to do the same thing here, except we have e cubed instead of log. So I'm scrolling all the way down. Here goes. Now I'm there. Let's put the x's on the left-hand side for the x's, and the terms that do not have x's in them, let's get those together on the right-hand side. So I'm going to subtract x from both sides to get the terms with x's in them together on the left, and I'm going to add e cubed to both sides to get the terms without x's in them together on the right-hand side. So on the left, we're going to have x e cubed minus x. On the right, anyone have a preference between 4 plus e cubed and e cubed plus 4? All right, I'm going to go with e cubed plus 4. On the left, like we did way up high, factor out an x. Each term has a factor of x, so we can factor out an x and write it x times e cubed minus what? 1. Good. Equals e cubed plus 4. And final step, prior to punching this into the calculator, divide both sides by e cubed minus 1, and we will end up with x equals e cubed plus 4 over e cubed minus 1. Now, it might be good to leave this as the final answer, except that we have to take this, add 4 to it, and subtract 1 from it, and make sure both those quantities are positive. So we really, in order to check it, we have to punch this into a calculator to make sure those quantities are in fact positive. So here goes. It's going to be second. Actually, begin by opening the parentheses if you want a single sequence of keystrokes. It's going to be left parenthesis. So clear my key press history and try that again. Left parenthesis, second ln, that gives e to a power of 3. Close the parentheses for the exponential function, and then add 4 and close parentheses for the numerator. Divided by, open parenthesis, second ln, e to the third power, close the parentheses, and then minus 1, and then close the parentheses. And press enter. 1.2620 if we round. 1.2620. If we add 4 to that, that's about 5.2620, and that's positive, so that's okay. We can take the log of that. If we subtract 1 from that, it's about 0.2620, but still positive, so we can take the log of that. So this is going to be our solution, 1.2620.